Hi there, enclosure enthusiasts, and welcome back to the Enclosure Institute. I'm Phil Taylor.
And I'm Jimmy Budd. In previous videos and blogs, we've spent a lot of time talking about material selection for your enclosure gasket. We've also spent a little bit of time discussing recommendations for the geometric design of that gasket. Today we want to offer some insights into the various manufacturing processes that are commonly used to produce those gaskets and why it matters.
There's always more than one way to skin a cat. But hey, wait a minute. If you're a cat lover, no offense intended. It's just that there's a myriad of ways to produce a gasket for enclosures. Why don't you mention a few, Jimmy?
Well, for starters, without incurring tooling costs or doing any harm to the animal kingdom, we can use lasers or water jets to cut customer-designed shapes. No punch or die is required. We often use a customer-provided CAD file, or in some cases, we may be able to create the CAD from other details supplied by the customer.
This is a very good process for creating prototypes or proof of concept parts in small quantities. However, it can be slow in cutting if the geometry is complex. Think of the laser or water jet beam as a pencil point as it meticulously draws each line of the part one at a time. It may be more time-consuming in cutting of each part, but without the cost of tooling or the time it takes to make the tool, this becomes a very efficient way to produce a gasket.
Another very common method used to cut gaskets is steel roll die cutting. Steel roll dies are most often constructed of steel blades set in wood. Flatbed punch presses of many types are used to force the blades through the chosen material. And even with steel roll dies, the cutting depth of the blade is a variable that we can control. Of course, as is true of all dies, the cost of the die is dependent on the complexity of the geometry and the amount of the cutting surface, but comparatively speaking, steel roll dies are usually very inexpensive.
The precision that a steel roll die can achieve is usually adequate for foam gaskets. However, if your gasket design requires very precise tolerances, a matched metal die may be needed. Matched metal dies involve two complementary die components, a male punch and a female die that are matched in pinpoint unison. While much more expensive than a steel roll die, they're not only more accurate, they're also more durable.
Next, let's talk about Marian's bread and butter, rotary die cutting. Rotary die cutting is a very popular method of converting and is an age-old proven method of efficiently cutting labels, paper goods, band-aids, and other everyday products, but it can be used to cut gaskets when the design fits. The rotary die is machined and etched from steel cylinders to produce the custom shape when rolled across the gasket material. There are limitations in the thickness and hardness of the gasket materials that can be used, but the cost of a rotary die is relatively low, and the speed at which it can produce small parts is very efficient.
That describes a few of the methods a converter like Marian might use to produce your enclosure gasket, and I'll bet you're now wondering, so how do you make the choice on which process to use? To answer that question, we need more information.
There are several factors that come into play and affect a decision for which cutting method best suits the production of your part. We'll cover each in more detail, but here are a few things we consider. First, what material is to be cut? That is, what is the hardness, thickness, number of layers, and so on. Second, what is the required volume of parts? Do you need hundreds, thousands, or even millions of parts? Or maybe you just need a handful when prototyping. Next, what is the precision needed? Do you have very tight tolerances that must be maintained? Moving on, and something that's not considered as often is the packaging of the gasket for delivery to the assembly location. Will your parts be delivered to you loosely in a box, kiss cut on a roll, cut into singulated pads, or something else? And finally, what is the method of assembly? That is, how will the gasket be installed into your device? By hand, automation, or maybe a combination of both? Now, we'll take a closer look at these.
Most foam materials are never too hard for any die cutting method, but they may be too thick for rotary die cutting. Some foam materials are only manufactured in sheets and therefore are poor choices for rotary die cutting. Silicone materials resist cutting by simple lasers, but are cut very well by waterjet.
As we said, laser and waterjet are targeted to low-volume prototypes, but for some materials and small geometries, lasers can achieve high precision. Steel roll dies often suffice for medium volumes, but the higher cost of matched metal rotary dies can be washed away by the increased speed and efficiency of production.
If your application involves very tight tolerances for the gasket to function as designed, we'd want to work together to understand where and how that precision is needed. We can design the cutting tool to support that need.
For example, in a rotary die, we may choose to design a critical dimension across the die rather than around the die for tighter control of that dimension. A matched metal die can be designed to hold much tighter tolerances than a steel roll die.
Together, we decide how to best package the gaskets to get them to your assembly location without any deformations during transit or storage. Foam gaskets that are not packaged properly can be easily creased, compressed, bent, stretched, or deformed in other ways. We package all parts in polyline containers to protect against environmental elements, but we need to go beyond that level to ensure that the part comes out of the box looking the same as it did when it went in.
We call this designing for manufacturing, and this is something we like to work with our customers on early in the design process to improve efficiency during their handling and assembly. You can design a great gasket made from excellent materials, but if you can't get that gasket in the right place efficiently time after time, you'll probably have a failure sooner or later. If your assembly process is manual, you might want the gasket supplied as individual parts with a pull tab or halo tab on the adhesive liner, or you may want the parts kiss cut and supplied with rolls for easy peel off. Or maybe your assembly will be done robotically. We need to work with your equipment designer and programmer to understand how the part will be picked and placed, but can produce parts that will seamlessly integrate with your equipment.
Back in Module 2, we discussed gasket designs made from multiple pieces, such as strip gaskets. These are most often used to seal very large enclosures where a one-piece gasket would be cost prohibitive. But as we said then, and it's probably obvious, the joints of the multi-piece gasket create potential leak paths if not carefully installed. So as the producer of the multi-piece gasket, a converter like Marian will need to understand how you will assemble the gasket and how you will want the multiple pieces presented to your assembly process. There's no right or wrong or one way for it to be done. Some customers design each component separately and want them purchased and supplied independently. Others design a kit or group components to be supplied as a single unit. But the choice affects the tool design that your converter will need to produce the gasket.
There's also another gasket assembly option available that doesn't involve die cutting at all. Your gasket may be able to be formed or cured in place. For the sake of our discussion, a form-in-place gasket is a one-part RTV elastomer dispensed onto the flange of the gasket location. It can be, and most often is, assembled while viscous before completely curing. The elastomer will cure in place at ambient temperatures. These RTV products can be dispensed manually, but are more often dispensed robotically. The cure-in-place gasket is very similar, but is most often composed of a two-part liquid system that is robotically applied through dedicated pump and mixing CNC equipment. The difference is that the compound being dispensed needs to be exposed to a curing process of heat or UV exposure after application and before the assembly can be completed.
Comparing form or cure-in-place gaskets to one-piece die-cut gaskets, the first and probably obvious advantage of the dispensed gasket is the cost of the individual gasket. Without the cost of the center, the form-in-place gasket requires much less material. On the flip side, disadvantages of the form or cure-in-place gasket are the upfront cost for the dispensing and curing equipment, programming, and the assembly setup, which add up quickly. The time required for equipment maintenance, flushing, and cleaning at the end of the run is another expense that is not required when applying die-cut gaskets. For these reasons, form-in-place or cure-in-place becomes advantageous only for very high-volume applications.
The choice of elastomers available as form-in-place or cure-in-place is somewhat also limited, although both urethane and silicone materials are options. Silicones are the most common, and many of those silicone options are either silver-filled for EMI applications or carbon graphite-filled for thermally conductive applications. With these last two being some of the most expensive elastomeric choices, it's easy to understand the desire to reduce the cost of the elastomer in the gasket.
Reworkability varies significantly. Die-cut foam gaskets are easy to rework. Depending on the shape, location, and the elastomer, some cure-in-place gaskets can be reworked. However, reworking is nearly impossible for formed-in-place gaskets.
Another consideration should be the shelf life. Fully cured foam materials that will be die-cut for gaskets have very long or unlimited shelf life. On the other hand, the liquid components used to make cure or form-in-place gaskets have very limited shelf life recommendations. Controlling inventory and waste may be a problem or an unforeseen expense.
Well, that about does it for me, Jimmy. I'm even tired of hearing myself talk. Can't imagine what the viewers are thinking.
Well, the same thing I am. It's time for you to sign off.
Till next time, I'm Phil Taylor.
And I'm Jimmy Budd. See you then.